What if I told you that right now, at this very moment, there are galaxies racing away from us at 5 times the speed of light? And not only is this happening, but it's completely allowed by Einstein's theory of relativity, the same theory that says nothing can travel faster than light. Your brain just short-circuited a little, didn't it? Because that sounds like a complete contradiction. It sounds impossible. But here's the thing that's going to absolutely shatter everything you thought you knew about the universe. Both statements are true. Light is the cosmic speed limit. Nothing can break it. And yet, vast chunks of the universe are right now moving away from us faster than light could ever travel. This isn't science fiction. This isn't speculation. This is the universe we actually live in. And the explanation for how this works is so mind-bending that when you truly understand it, you'll never look at space, time, or reality itself the same way again. I'm going to take you on a journey today that will fundamentally change how you see everything. By the end of this video, you're going to understand one of the most profound truths about our cosmos, a truth that most people will go their entire lives never grasping. And here's what makes this so incredible. The answer to this paradox reveals something so beautiful about the nature of existence that it borders on the spiritual. Before we dive into this rabbit hole together, do me a favor, hit that like button and subscribe, because what we're about to explore is going to take some serious brain power, and I need to know you're committed to this journey. Also, drop a comment telling me where in the world you're watching from and what time it is for you right now. I'm genuinely curious how far and wide this cosmic knowledge is spreading. Are you watching from Tokyo at 3 a.m.? London during your lunch break? Los Angeles before sunrise? Let me know. Now, let's blow your mind. Think about what you learned in school about the speed of light. You were probably told it's the ultimate speed limit of the universe, 299,792,458 meters per second, or about 186,000 miles per second. Nothing can go faster. Einstein proved it. End of story. And for the most part, that's true. If you tried to accelerate a spaceship to the speed of light, you'd need infinite energy. It simply cannot be done. The laws of physics won't allow it. But here's where things get weird. When astronomers look out into deep space with our most powerful telescopes, they see galaxies that are currently more than 46 billion light years away from us. Now, stop and think about that for a second. The universe is only 13.8 billion years old. If nothing can travel faster than light, how on earth, or should I say, how in the universe can something be 46 billion light years away when the universe hasn't even been around for 46 billion years? The light from those galaxies has only had 13.8 billion years to travel. So they should be, at most, 13.8 billion light years away, right? But they're not. They're more than 3 times that distance. The math doesn't work. Unless something very strange is happening. Here's the shocking revelation that's going to set the stage for everything else we discuss. Space itself is expanding. Not expanding into anything, just expanding. And when space expands, it carries galaxies along with it, like raisins in rising bread dough. And here's the kicker. There is no speed limit on how fast space itself can expand. Let me say that again, because it's crucial. Objects moving through space cannot exceed the speed of light. But space itself expanding? That can happen at any speed. And it is, right now, all around us. This is the loophole in Einstein's cosmic speed limit. This is how the universe cheats. And understanding this loophole is going to take us on a journey through some of the most mind-bending concepts in all of physics. We're going to explore what space really is, what expansion actually means, how we can see things moving faster than light without violating relativity, and what this means for the ultimate fate of our universe. Buckle up. This is going to be one hell of a ride. Let's start with the basics, but I promise you, even the basics are going to surprise you. First, we need to understand what we really mean when we talk about the speed of light. Most people think of it as just a really fast speed, the speed that light happens to travel at. But that's not quite right. The speed of light is something much more fundamental. It's not really about light at all. In 1905, Albert Einstein published his special theory of relativity, and buried in that theory was a revolutionary idea. There's a maximum speed at which information can travel through the universe. Any information, any cause leading to any effect. And that speed happens to be exactly the speed that light travels in a vacuum. But light isn't special because it's fast. Light travels at that speed because it has no mass. The speed limit of the universe is really about the structure of space-time itself. Think of it like this. Imagine space-time is a fabric with a certain stiffness to it. That stiffness determines how fast ripples information, cause and effect, can propagate through it. Light just happens to be one of the things that travels at that maximum speed. But it's the speed limit that's fundamental, not the light. Here's where it gets interesting. When Einstein says nothing can travel faster than light, what he really means is that nothing can move through space faster than light. That's a crucial distinction. Moving through space is different from space itself changing. Imagine you're on a moving walkway at an airport. You can walk along the walkway at your own speed, let's say 3 miles per hour. That's you moving through space. But the walkway itself is also moving maybe at 2 miles per hour. So relative to the ground, you're moving at 5 miles per hour, even though you're only walking at 3. Now, imagine there's a speed limit on the walkway. You can't walk faster than 3 miles per hour. That's the rule. But what if the walkway started moving at 10 miles per hour? You wouldn't be breaking the speed limit by walking at 3 miles per hour, even though you'd be moving at 13 miles per hour relative to the ground. You're still obeying the local speed limit. It's the walkway that's moving fast, not you. That's essentially what's happening in the universe. Galaxies aren't moving through space faster than light, but space itself is expanding, carrying those galaxies with it. And the expansion of space doesn't have to obey the speed limit that applies to things moving through space. Now, you might be thinking, okay, but how do we know space is actually expanding? How do we know it's not just galaxies moving away from each other through static space? Great question. And the answer comes from one of the most important discoveries in the history of science, made by a man whose name you've probably never heard. Edwin Hubble. In 1929, Edwin Hubble, yes, the Hubble Space Telescope is named after him, made an observation that changed everything. He was studying distant galaxies, measuring how fast they were moving relative to Earth. He did this by looking at the light from these galaxies and measuring something called redshift. Here's how that works. When an object is moving away from you, the light waves from that object get stretched out, shifting toward the red end of the spectrum. The faster it's moving away, the more redshift you see. This is the Doppler effect, the same phenomenon that makes an ambulance siren sound different as it drives past you. Hubble measured the redshift of dozens of galaxies and made a shocking discovery. Every galaxy he looked at was moving away from us. Every single one. And not only that, but the farther away a galaxy was, the faster it was receding. He found a direct relationship. Double the distance, double the speed. Triple the distance, triple the speed. This was stunning. If galaxies were just moving randomly through space, you'd expect to see some moving toward us and some moving away. But they were all moving away, and the relationship between distance and speed was perfectly linear. There was only one explanation that made sense. The space between galaxies was expanding. The universe itself was growing. Think about this. You're not at the center of the universe. No one is. Every observer, anywhere in the universe, would see exactly the same thing Hubble saw, all distant galaxies receding, with speed proportional to distance. This is only possible if space itself is expanding everywhere, all at once. Here's an analogy that really drives this home. Imagine a balloon with dots on it. As you blow up the balloon, every dot moves away from every other dot. If you were an ant sitting on one of those dots, you'd see all the other dots moving away from you. And the dots that are farther away would appear to be moving faster, simply because there's more expanding balloon surface between you and them. But here's the key. No dot is special. Every dot sees the same thing. The balloon itself is expanding. That's our universe. We're living on the surface of an expanding balloon, except instead of a two-dimensional surface expanding in three-dimensional space, we have three-dimensional space expanding in. Well, that's where things get really weird, and we'll come back to that. For now, here's what you need to understand. Hubble's discovery proved that the universe is expanding. And if it's expanding now, that means it was smaller in the past. If you run the clock backward, the universe gets denser and hotter until you reach a point about 13.8 billion years ago, when everything was compressed into an incredibly hot, dense state. This is what we call the Big Bang, though that's actually a terrible name. It wasn't an explosion in space. It was the expansion of space itself, starting from an incredibly dense initial state. Now, the rate at which the universe expands is described by something called the Hubble constant, named after Edwin Hubble. And this is where things start to get really interesting for our main question about faster-than-light expansion. The Hubble constant tells us how fast space is expanding. The current best measurements put it at about 70 kilometers per second per megaparsec. Now, I know that sounds like gibberish, so let me translate. For every 3.26 million light-years of distance, space is expanding at an additional 70 kilometers per second. So a galaxy that's 3.26 million light-years away is receding at 70 kilometers per second. A galaxy twice that distance away is receding at 140 kilometers per second. A galaxy 10 times that distance is receding at 700 kilometers per second. Here's where your brain should start tingling. The speed of light is about 300,000 kilometers per second. So if we do the math, any galaxy that's more than about 14 billion light-years away is receding from us faster than the speed of light. And as I mentioned at the start, we can observe galaxies more than 46 billion light-years away. Those galaxies are receding from us at speeds several times the speed of light. And here's what's going to blow your mind. This doesn't violate relativity at all, not even a little bit. Einstein's theory is perfectly fine with this. Because remember, Einstein's speed limit applies to objects moving through space, not to space itself expanding. But wait, you might be thinking, if those galaxies are moving away from us faster than light, doesn't that mean we can never see them? How do we even know they exist? This is such a good question, and the answer reveals something profound about the nature of expansion in light. Here's the thing. Those distant galaxies were not always receding faster than light. In the early universe, when they were closer to us, they were receding slower than light. So the light they emitted back then was able to make progress toward us, even though space was expanding. Think of it like a fish swimming upstream in a river. If the river current is slower than the fish can swim, the fish makes progress upstream. But if the current gets faster than the fish can swim, the fish starts getting swept backward, even though it's still swimming as hard as it can. Light from distant galaxies is like that fish. In the early universe, when those galaxies were closer, the expansion rate between us and them was slow enough that their light could make progress toward us. As the universe expanded and the distances grew, the recession speed increased, but by then, the light was already on its way. It's been traveling toward us for billions of years, fighting against the expansion of space, and finally reaching us now. But here's the really wild part. There are galaxies even farther away, so far away that they're receding so fast that their light will never reach us. Ever. Not even if we wait for the entire age of the universe over again. These galaxies are beyond what we call the cosmic horizon, and they are forever beyond our ability to observe. As far as physics is concerned, they might as well not exist, because no information from them can ever reach us. They are causally disconnected from us, permanently. Let that sink in. There are parts of the universe that we will never, ever see or interact with in any way, no matter how long we wait or how advanced our technology becomes. Not because they're far away, but because the space between us is expanding so fast that it creates an impassable barrier. This should strike you as deeply weird. We're talking about a speed limit that can't be broken except when it can. We're talking about parts of the universe that exist but are completely inaccessible to us. We're talking about space itself having properties and behaviors that are totally counterintuitive. And we've only just scratched the surface. Because now we need to ask, if space is expanding, what exactly is space? What does it mean for nothing to grow? Can empty space really expand? And what is it expanding into? These questions are going to take us into some of the deepest mysteries in physics. But before we go there, I want you to take a moment and really sit with what we've discussed so far. The universe is not static. It's growing everywhere, all at once. Distant galaxies are racing away from us faster than light could ever travel, and yet this doesn't violate the fundamental laws of physics. We live in a universe with a cosmic horizon beyond which we can never see, a permanent limit to our knowledge. This is real. This is happening. And if you're feeling a bit dizzy, that's exactly how you should feel. Because we're about to go even deeper, and things are about to get a lot stranger. Stay with me. The best part is still coming. Now that we understand that space is expanding, and that this expansion can carry galaxies faster than light, we need to dive into what might be the most mind-bending question of all. What is space, really? This question has haunted physicists for centuries, and the answer turns out to be far stranger than almost anyone imagined. Most people think of space as just emptiness, the nothing between things. It's the absence of stuff, the vacuum. But here's where modern physics takes a sharp turn into the bizarre. Space is not nothing. Space is something. It has properties. It can bend, twist, expand, and even vibrate. Empty space has energy. It has structure. It is, in a very real sense, a physical substance. This idea goes all the way back to Einstein's general theory of relativity, published in 1915. Einstein showed that what we call space and time are not separate things, but are woven together into a single four-dimensional fabric called spacetime. And this fabric isn't just a passive stage on which events occur. It's an active participant in the physics. Mass and energy bend spacetime, and that bending is what we experience as gravity. Think of it like this. Imagine a stretched rubber sheet. If you place a bowling ball on the sheet, it creates a depression. Now roll a marble near the bowling ball. The marble will curve toward the bowling ball, not because there's a force pulling it, but because it's following the curves in the rubber sheet. That's essentially how gravity works in Einstein's theory. The Earth curves space-time around it, and you're following those curves, which is why you feel pulled toward the ground. This was revolutionary enough. But then Einstein realized something even more profound. If space-time is a thing, a fabric with properties, then that fabric can change. It can ripple, creating gravitational waves. It can expand. It can contract. And most importantly for our discussion, it can expand uniformly everywhere, causing all distances to grow. When cosmologists talk about the expansion of the universe, they're not talking about galaxies flying apart through static space. They're talking about the actual metric of space, the distances between points, getting larger over time. New space is being created everywhere, all the time. Now you might be thinking, wait, if new space is being created, where is it coming from? What's it made of? And this is where we hit one of the deepest mysteries in physics. The honest answer is, we don't really know. General relativity describes how space-time behaves, but it doesn't explain what space-time fundamentally is. It's like having a detailed manual for how to drive a car without understanding what an engine is. Some physicists think space-time might emerge from more fundamental quantum structures, that space and time are not elementary, but are built up from something more basic. Others think space-time might be fundamental itself. We simply don't know yet. But what we do know is that space-time behaves like a physical substance, and that substance can expand. Here's what's absolutely crucial to understand. When space expands, it's not expanding into anything. This is probably the single hardest thing for people to wrap their heads around. Our brains want to imagine the universe as a balloon expanding into a room. But that's not right. There is no room. There is no outside. The universe is all there is. When we say space is expanding, we mean that the distances between objects are increasing. Period. There's no extra-dimensional space that the universe is expanding into. Think about it this way. Imagine you're a two-dimensional being living on the surface of a balloon. You can move forward, backward, left, and right, but you have no concept of up or down off the surface. As the balloon inflates, every point on the surface gets farther from every other point. But from your two-dimensional perspective, there's no outside the balloon. The surface is your entire universe. It's expanding, but not into anything. The metric of the surface itself is just getting bigger. That's analogous to our situation, except we're three-dimensional beings living in a three-dimensional space that's expanding. There might be higher dimension. String theory suggests there could be as many as 11, but if they exist, they're either curled up too small to notice, or they're not accessible to us in any way we can detect. For all practical purposes, our three-dimensional space is all there is, and it's getting bigger. Now, here's where things get really interesting. If space is a thing, and that thing can expand, then we need to ask, what controls how fast it expands? Why is the Hubble constant what it is, and not some other value? And has the expansion rate always been the same? The answer to that last question is a resounding no. The expansion rate has changed dramatically over the history of the universe, and understanding why brings us to one of the most shocking discoveries in modern cosmology. In 1998, two teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were studying distant supernovae to measure how the universe's expansion has changed over time. They expected to find that the expansion was slowing down. After all, gravity pulls everything together, so it should be acting as a brake on the expansion, gradually slowing it over billions of years. But that's not what they found. To their absolute shock, they discovered that the expansion of the universe is accelerating, not slowing down, speeding up. Distant galaxies are receding from us, not just faster than nearby ones, but they're accelerating away. The universe is expanding faster now than it was a billion years ago, and faster then than it was a billion years before that. This discovery won Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011, and it has been described as the most important cosmological discovery since Hubble's finding that the universe is expanding at all. Because here's the thing, we have no idea why the expansion is accelerating. Or rather, we have a name for it, dark energy, but that name doesn't explain anything. It's just a label for our ignorance. Something is pushing the universe apart, something that acts like an anti-gravity force filling all of space. And it makes up about 68% of the total energy content of the universe. And we don't know what it is. Let me put this in perspective. Everything you've ever seen, touched, or interacted with, every atom in your body, every star in the sky, every galaxy in the observable universe, all of that normal matter makes up less than 5% of what's out there. Another 27% is dark matter, which we also don't understand, but at least we can detect its gravitational effects. And the remaining 68%? That's dark energy. That's the mysterious thing accelerating the expansion. Here's what really should blow your mind. If dark energy remains constant or gets stronger, which current observations suggested, will then the acceleration of the universe's expansion will continue forever? In the far future, the expansion will get so fast that eventually even nearby galaxies will be receding faster than light. The Milky Way and our local group of galaxies will remain gravitationally bound together, but everything else will disappear beyond our cosmic horizon. In trillions of years, a civilization arising in our galaxy would look out at the universe and see nothing, just darkness, no other galaxies, no cosmic microwave background radiation, no evidence that the Big Bang ever happened. They would have no way of discovering that the universe is expanding, because everything that could teach them that would be gone receded beyond the horizon. From their perspective, the universe would be just our galaxy, an empty space forever. Isn't that haunting? We live in a special time in cosmic history, one of the only epochs where the expansion is fast enough to be measurable, but slow enough that we can still see a universe full of galaxies. We're living in the narrow window where the universe can be understood. Future civilizations won't have that luxury unless they inherit our knowledge. But let's bring this back to our central question. How does all this relate to faster-than-light expansion? Well, here's the key. The acceleration of expansion means that more and more of the universe is crossing the threshold into the faster-than-light regime. Objects that are currently receding from us slower than light will, given enough time, end up receding faster than light. The cosmic horizon is not static. It's growing, but not as fast as the universe is expanding. More and more of the universe is becoming forever inaccessible to us. And here's something that should really bake your noodle. There are galaxies we can see right now whose light will never reach us again. We're seeing them because we're receiving light they emitted billions of years ago when they were closer and receding slower than light. But they've since crossed the horizon. If we tried to send a light signal to them right now, it would never arrive, ever. The space between us is expanding too fast. We are, in a very real sense, looking at ghosts. Echoes of galaxies that, from our perspective, might as well not exist anymore because we can never interact with them again? This brings us to a profound question. What does it mean for something to exist if it's beyond our cosmic horizon? This isn't just philosophy. It's a real physical question. In physics, things that are causally disconnected, that can never exchange information or influence each other, are in some sense in different universes. They're separate realities. So when we talk about the universe, do we mean everything that exists, or just the observable universe, the part within our cosmic horizon? These are increasingly being recognized as different concepts. The universe might be infinite, but our observable universe is finite and getting smaller in terms of what's accessible to us. Now, I want to address something that might be bugging you. If space is expanding everywhere, why aren't we expanding? Why isn't the Earth expanding? Why isn't your body expanding? If new space is being created everywhere, shouldn't everything be getting bigger? This is a great question, and the answer reveals something crucial about how expansion works. The expansion of space only becomes significant on scales where other forces are negligible. Inside atoms, the electromagnetic force is far too strong for expansion to matter. Inside your body, chemical bonds hold everything together. On Earth, gravity and electromagnetic forces keep things the size they are. Even in our solar system, gravity keeps the planets in their orbits. Expansion only dominates on scales of hundreds of millions of light years, the distances between galaxy clusters. On those scales, the gravity of individual galaxies is too weak to resist the expansion, so space carries them apart. But anything held together by other forces like galaxies themselves, or anything smaller, is unaffected by expansion. Think of it like this. Imagine you have a rubber sheet with coins glued to it at various points. As you stretch the rubber sheet, the space between the coins grows, but the coins themselves don't stretch because they're held together by their own rigidity. They just drift apart as the rubber between them expands. That's what's happening in the universe. Galaxies are the coins. Space is the rubber sheet. The expansion of space carries galaxies apart, but the galaxies themselves, held together by gravity, don't expand. And certainly nothing smaller than a galaxy expands. So you can relax. you're not expanding. The expansion of the universe is not going to rip apart your body or the Earth or the solar system, but it is, slowly and inexorably, carrying distant galaxies away from us at ever-increasing speeds. Now, let's talk about what happens when we try to reconcile this expanding universe with Einstein's special relativity, the theory that gives us the cosmic speed limit in the first place. Because here's where things get really subtle and interesting. Special relativity says that nothing can travel through space faster than light. It also says that the speed of light is the same for all observers, no matter how they're moving. These two facts together have some very strange consequences. For instance, time slows down for objects moving at high speeds. If you traveled on a spaceship at 99% the speed of light, time would pass much more slowly for you than for people on Earth. This is called time dilation, and it's been confirmed by countless experiments. But here's the thing, special relativity only applies in flat, unchanging spacetime. It describes physics in the absence of gravity and in the absence of spacetime curvature or expansion. When spacetime itself is curved or expanding, you need general relativity, which is a more complete theory that includes special relativity as a special case. In general relativity, the rule is this: you can't overtake a light beam. Locally, nothing can go faster than light. If you're sitting next to a light beam, you can never catch up to it or pass it, no matter what. But on cosmological scales, where space itself is changing, you can end up getting separated from distant objects faster than light could travel. Here's an analogy that might help. Imagine you're on a really long treadmill, and you're trying to reach someone who's on the treadmill ahead of you. You can run at a maximum speed, let's say 10 miles per hour. That's your speed limit. You can't go faster. Now, as long as the treadmill is moving slower than 10 miles per hour backward, you can make progress toward the person ahead. But if the treadmill starts moving backward at 15 miles per hour, you'll start getting farther from them, even though you're running as fast as you can forward. You're not breaking your speed limit. You're still only running at 10 miles per hour relative to the treadmill. But relative to the room the treadmill is in, you're moving backward. That's what's happening with light in an expanding universe. Light is always traveling at the speed of light relative to the space around it. That never changes. But if space itself is expanding faster than light can compensate for, then distant objects end up getting farther apart, faster than light can travel. Crucially, if you were traveling alongside that light beam, you'd still measure it moving away from you at exactly the speed of light. Special relativity's rules still apply locally. It's only when you measure velocities across vast, expanding distances that you can end up with recession speeds faster than light. This is why physicists say that the cosmic speed limit isn't being violated. The rules of relativity are still in force everywhere, locally. It's just that on cosmological scales, the expansion of space allows for separations that increase faster than light. Now, here's a question that should be bothering you. If distant galaxies are receding faster than light, what happens to the light they're emitting? Can we ever see it? And if we can't, how do we know those galaxies even exist? This is where the concept of the cosmic horizon comes in, and it's one of the most important ideas in cosmology. Let me explain how this works, because it's both beautiful and deeply strange. Imagine a galaxy that's currently beyond our cosmic horizon, so far away that it's receding faster than light. This galaxy emits light in all directions, including toward us. But that light, as it travels through space, is swimming upstream against the expansion. In the region of space around that galaxy, the expansion is so rapid that the light is actually losing ground. It's like our fish swimming upstream in a river that's flowing faster than it can swim. Now, here's the key. As that light travels toward us, it's entering regions of space where the expansion rate is slower, because remember, expansion rate is proportional to distance. The farther the light gets from that distant galaxy, the slower the expansion rate becomes in the regions it's traveling through. Eventually, if the light can persist long enough, it will reach a region where the expansion is slower than light speed, and from that point on, it makes progress toward us. So even light from beyond the cosmic horizon can eventually reach us, but only if the horizon is expanding. And this is exactly what happens in our universe. The cosmic horizon is expanding faster than the universe itself, which means that we're continuously receiving light from galaxies that were previously beyond our horizon. However, and this is crucial, if the universe's expansion continues to accelerate, eventually the cosmic horizon will stop growing or even start shrinking. At that point, galaxies that cross the horizon will be lost to us forever. We'll never receive any more light from them. They will fade from view and disappear, one by one, as they cross the event horizon of the observable universe. This brings us to one of the most profound implications of cosmic expansion. The universe has an event horizon, much like a black hole. Anything beyond that horizon is causally disconnected from us. We can never send or receive signals from it. We can never visit it. It might as well be in a different universe. And here's what should really make you pause. We don't know if there's anything special about that horizon. It's completely arbitrary from the universe's perspective. It's just the boundary of what's observable from our particular location. An alien civilization in a galaxy 10 billion light-years away has a completely different cosmic horizon from us. They can see things we can't, and vice versa. This means that the idea of the universe becomes observer-dependent. Your observable universe is different from mine if we're in different locations. The universe is not a single, well-defined thing that everyone can agree on. It's a patchwork of overlapping observable regions, each centered on a different observer. This is reminiscent of the horizon around a black hole. If you're falling into a black hole, there's a point the event horizon, beyond which you can never send information back out. But from your perspective, nothing special happens as you cross that horizon. You don't feel anything unusual. It's only observers far from the black hole who see you frozen at the horizon, unable to proceed further. Similarly, if you could somehow travel to a galaxy beyond our cosmic horizon, you wouldn't notice anything special as you crossed it. From your perspective, the universe would look pretty much the same. But observers back on Earth would see you fade away, your light getting redshifted into invisibility as you crossed the horizon. This raises a fascinating question. Is there a sense in which the Big Bang itself is a kind of horizon not in space, but in time? We can't observe anything from before the Big Bang, much like we can't observe anything beyond the cosmic horizon. Both are fundamental limits to our knowledge imposed by the structure of spacetime. Some physicists think that what we call the Big Bang might not have been the actual beginning of the universe, but just the beginning of our observable patch of it. Maybe the universe is eternal, and the Big Bang was just a transition from some previous state. Maybe there are other regions of space beyond our horizon where different Big Bangs happened at different times. These are the ideas behind concepts like eternal inflation and the multiverse, which we'll touch on later. But before we go there, I want to make sure you really deeply understand the central paradox we've been exploring. How can things move faster than light without violating relativity? Let me give you one more way to think about this that might make it click. Special relativity says that the speed of light is constant for all observers. No matter how fast you're moving, you always measure light traveling at exactly 299,792,458 meters per second. This is the foundation of the theory, and it leads to all the weird consequences like time dilation and length contraction. But here's the subtle point. This is true for local measurements. If you're standing next to a light beam with a ruler and a stopwatch, you'll measure it going by at the speed of light. Always, without fail. The expansion of the universe doesn't change that. What expansion does is change the relationship between local measurements and global distances. In a static universe, if you measure the distance to a galaxy, and then measure how long light takes to reach you from that galaxy, you can calculate the speed of light by dividing distance by time, and you'd get the expected answer. But in an expanding universe, By the time the light reaches you, the galaxy is no longer where it was when the light was emitted. The distance has changed. So if you naively divide the current distance by the light travel time, you get a number that doesn't make sense. You might even get a number faster than light, but this doesn't mean anything is actually traveling through space faster than light. It just means you're comparing measurements made at different times in an expanding universe, and that's a tricky business. This is why cosmologists have to be very careful about how they define distances in an expanding universe. There are multiple ways to define distance proper distance: comoving distance, luminosity distance, angular diameter distance, and they all give different answers. The expansion of the universe means that distance is not a simple, well-defined concept anymore. Think about it. What does it mean to say a galaxy is 1 billion light years away? Does that mean it's at the location where light from it would take 1 billion years to reach us? But the galaxy isn't at that location anymore. It's receded during the 1 billion years the light was traveling. So do we mean where it was when the light was emitted? Or where it is now? Or something else? These questions don't have obvious answers. Distance in an expanding universe is genuinely ambiguous. And that ambiguity is at the heart of why faster-than-light recession is possible without violating relativity. We're not comparing apples to apples. We're comparing local measurements, which always respect the light speed limit, to global separations, which can change faster than light because space is expanding. All right, let's take a breath. I know that was a lot. We've covered the expansion of space, the nature of spacetime, dark energy, cosmic horizons, and the subtleties of how all this relates to special relativity. If your brain feels a bit stretched, pun intended, that's perfect. You're exactly where you should be. Before we move into the next section, where things are going to get even more mind-bending, I want you to really absorb what we've established. The universe is not a static backdrop. It's a dynamic, evolving entity. Space itself is a thing with properties, and one of those properties is that it can expand, carrying distant galaxies faster than light in the process. This doesn't violate Einstein's cosmic speed limit, because that limit only applies to motion through space, not to the expansion of space itself. And here's why this matters, why this isn't just an abstract puzzle for physicists to ponder. Understanding cosmic expansion is fundamental to understanding where we came from, where we're going, and what the ultimate fate of everything we know and love will be. It's about understanding our place in the cosmos, our relationship to the very fabric of reality. Stay with me. The journey is far from over, and the most mind-blowing revelations are still ahead. Now we need to dive into one of the most profound and strange implications of cosmic expansion: the Big Bang itself. Because if the universe is expanding, and we run the clock backward, we reach a point where everything was compressed into an infinitesimally small region of space. And that raises some absolutely wild questions. First, let's be clear about what the Big Bang was and wasn't. The Big Bang was not an explosion that happened at a point in space. This is the most common misconception, and it's completely wrong. There was no center to the explosion. There was no space outside the Big Bang into which the universe expanded. The Big Bang was the beginning of the expansion of space itself, happening everywhere simultaneously. Imagine you're watching a video of the expanding universe. You see galaxies moving apart from each other as space expands. Now, hit rewind. The galaxies get closer together. Space contracts. If you keep rewinding, you eventually reach a point where all the galaxies are on top of each other, where all the space between them has vanished, where everything is compressed into an impossibly hot, dense state. This is the Big Bang, not a single point, but a state of condition where all of space was compressed to near infinite density and temperature. And from our perspective, looking backward in time, this state was reached about 13.8 billion years ago. But here's where things get weird, really weird. When physicists talk about the singularity at the beginning of the Big Bang, they're talking about a point where the math breaks down. Density becomes infinite. Temperature becomes infinite. The laws of physics, as we understand them, cease to make sense. It's not that something dramatic happened there. It's that our theories can't tell us what happened. General relativity predicts a singularity, but when you get to conditions that extreme, quantum effects become important, and we don't have a theory that successfully combines quantum mechanics with general relativity. This is the holy grail of theoretical physics, a theory of quantum gravity that could tell us what really happened at the very beginning. String theory, loop quantum gravity, and other approaches are trying to answer this question, but we're not there yet. What we can say is this: at times earlier than about y-43 seconds after the Big Bang, that's the Planck time, the smallest unit of time that makes sense in our current theories, our understanding breaks down. We simply don't know what was happening. The universe might have been infinitely small and dense, or there might have been some quantum effect that prevented a true singularity. We don't know. But here's what we do know, and it's astonishing. From about 1 second after the Big Bang onward, we have a pretty good understanding of what happened. The universe was a hot, dense plasma of particles and radiation. As it expanded, it cooled. Protons and neutrons formed, then atomic nuclei. Eventually, about 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with nuclei to form atoms. At that moment, the universe became transparent to light for the first time. Before that, photons couldn't travel very far before scattering off free electrons. After that, light could travel freely through space. That light, the first light to travel freely through the universe, is still traveling today, and we can see it. It's called the cosmic microwave background radiation, or CMB, and it's one of the most important pieces of evidence we have for the Big Bang. Discovered, accidentally, by Arno, Penzias and Robert Wilson in 1964. A discovery that won them the Nobel Prize. The CMB is a faint glow of microwave radiation coming from every direction in space. It's the afterglow of the Big Bang, stretched and cooled by 13.8 billion years of cosmic expansion. When you tune an old TV to a channel with no signal and you see static, about 1% of that static is actually photons from the CMB. You're seeing the echo of the Big Bang with your own eyes. How wild is that? The CMB is remarkably uniform. It has almost exactly the same temperature, about 2.7 Kelvin, or minus 270 degrees Celsius in every direction. But not quite. There are tiny fluctuations, variations of about 1 part in 100,000. And those tiny fluctuations are incredibly important because they're the seeds from which all structure in the universe grew. In the early universe, some regions were slightly denser than others just barely. But gravity amplified those differences. Denser regions attracted more matter, becoming even denser. Over hundreds of millions of years, these overdense regions collapsed into the first stars and galaxies. The structure we see today, the cosmic web of galaxies, separated by vast voids, all grew from those microscopic fluctuations in the early universe. We've mapped those fluctuations with incredible precision using satellites like COBE, WMAP, and Planck. And the patterns we see match almost exactly what we'd expect from the physics of the early universe. It's one of the great triumphs of modern cosmology. We can look at the baby picture of the universe and understand how it grew into what we see today. But here's where things get really interesting for our discussion about faster-than-light expansion. The Big Bang itself was a period of incredibly rapid expansion. In the first tiny fraction of a second, the universe expanded by a factor that makes modern expansion look absolutely glacial by comparison. This period is called cosmic inflation, and it was proposed by physicist Alan Guth in 1980 to solve some puzzles about the Big Bang. The idea is that in the first 10 to 36 seconds or so after the Big Bang, the universe underwent a period of exponential expansion, doubling in size about every 10 to 37 seconds. In less than a blink of an eye far less the universe expanded by a factor of at least 1026. That's a 1 followed by 26 zeros. To put this in perspective, imagine a region of space the size of an atom expanding to the size of the entire observable universe in less time than it takes light to cross the nucleus of an atom. That's inflation. It's expansion on a scale and at a speed that absolutely dwarfs what we see today. During inflation, space was expanding far, far faster than light. Objects that were close together at the start of inflation ended up separated by vast distances so large that they're beyond each other's cosmic horizons. Light has not had time, even in 13.8 billion years, to travel between them. And here's the kicker. Inflation might still be happening, just not in our region of space. The theory of eternal inflation suggests that while inflation ended in our patch of the universe, it's still ongoing in other regions. In fact, it might be ongoing in an infinite number of regions, creating an infinite number of what we might call pocket universes, each with its own Big Bang, its own physical properties, possibly even its own laws of physics. This is the multiverse hypothesis, and it's one of the most controversial and mind-blowing ideas in modern physics. If it's true, then our universe, everything we can see or ever will see, is just one bubble in an infinite cosmic foam of universes. Most of those other universes are forever beyond our cosmic horizon, separated from us by regions of space that are still inflating at tremendous rates. Let me be clear, this is speculative. We have no direct evidence for the multiverse, and some physicists think it's untestable and therefore not science. But it's a natural consequence of our best theories of cosmic inflation, and it raises profound questions about the nature of reality, the meaning of probability, and our place in the cosmos. Think about what this means. If the multiverse is real, then faster-than-light expansion isn't just something happening at the edges of our observable universe. It's happening everywhere, in the vast inflating regions between pocket universes, carrying those universes away from each other at inconceivable speeds. Our universe might be one of countless others, all of them island bubbles in an eternally inflating sea. And here's something that should really make you pause. If inflation can happen, if space can expand exponentially fast, then the cosmic speed limit, the thing we started this whole discussion with, is even more flexible than we thought. During inflation, not only were distant objects receding faster than light, but nearby objects that started out right next to each other ended up on opposite sides of the observable universe. The expansion was so rapid that even light couldn't keep up. This brings us back to a question I posed earlier. What is space expanding into? If our universe is a bubble in a larger inflating region, does that mean there's something outside our universe? The answer is subtle. From the perspective of general relativity, each pocket universe is its own spacetime. The inflating region between pocket universes is not outside them in any spatial sense. It's dynamically disconnected from them. You can't travel from our universe to another pocket universe because the region between is expanding too fast. Even if you traveled at the speed of light, you'd never reach another universe. You'd be like a fish swimming upstream in an infinitely strong current. In that sense, other pocket universes don't exist for us. They're beyond our cosmic horizon, causally disconnected, forever inaccessible. From a practical, operational perspective, they might as well not exist. But from a theoretical perspective, from the God's eye view of the equations, they're there, just as real as our own universe. This raises deep philosophical questions. What does it mean to exist? If something can never be observed or interacted with in any way, is it real? These are questions that physics alone can't answer. They touch on metaphysics, on the nature of reality itself. But before we go down that rabbit hole, let me bring us back to something more concrete, the observable consequences of cosmic expansion in our own universe. Because while we can't test the multiverse hypothesis directly, We can test predictions about how expansion affects what we see. One of the most important consequences of expansion is redshift. Remember how I mentioned earlier that light from receding galaxies gets stretched out, shifting toward the red end of the spectrum? This is caused by the expansion of space. As light travels through expanding space, its wavelength gets stretched along with the expansion. The amount of redshift tells us how much the universe has expanded since the light was emitted. A galaxy with a redshift of 2, for example, means the universe has expanded by a factor of 3 since that light left the galaxy. It's redshift plus 1, if you want the exact factor. The most distant objects we've observed have redshifts over 10, meaning the universe has expanded more than tenfold since their light began its journey to us. Here's something beautiful. By measuring redshift, we're directly measuring the expansion of the universe. We're seeing the history of cosmic expansion encoded in the light from distant objects. It's like reading a history book where each galaxy is a chapter from a different time in the universe's past. And what we see is fascinating. At redshifts greater than about 1.5 corresponding to about 9 billion years ago, we see evidence that the universe's expansion was slowing down, as we'd expect from gravity acting as a brake. But at lower redshifts, in more recent times, we see the expansion accelerating. This is the dark energy signature that won Perlmutter, Schmidt, and Rees the Nobel Prize. The transition from deceleration to acceleration happened about 5 billion years ago. Before that, gravity was winning, slowing the expansion. After that, dark energy took over, driving acceleration. We happen to live in the era where dark energy has recently become dominant, and the universe is transitioning from a matter-dominated phase to a dark energy-dominated phase. This timing might not be a coincidence. Some physicists have speculated that we can only exist in this narrow window of cosmic history when the universe is old enough for stars and planets to form, but young enough that we can still see a universe full of galaxies. This is a version of the anthropic principle, the idea that we observe the universe to have certain properties, because if it didn't have those properties, we wouldn't be here to observe it. Whether or not you find anthropic reasoning convincing, it's undeniable that we live in a special time. In the past, the universe was too hot and dense for life. In the far future, dark energy will have pushed everything beyond our horizon, and the cosmos will be dark and empty. We exist in a narrow slice of time when the universe is observable. Now, let's talk about what all this means for the ultimate fate of the universe. Because if expansion continues to accelerate, driven by dark energy, then we can make some predictions about the far future. And they're not cheerful. In the long term, we're talking trillions of years. The acceleration of expansion will carry more and more galaxies beyond our cosmic horizon. Eventually, only the galaxies in our local group will remain visible. Everything else will have receded faster than light, disappearing into the void. But it gets worse. If dark energy remains constant or gets stronger, which current evidence suggests it might, then eventually, the expansion will become so rapid that even gravitationally bound structures start to get torn apart. First, galaxy clusters will unbind, then individual galaxies, then solar systems, then planets, then molecules, then atoms. This scenario is called the Big Rip, and it's one possible fate of the universe. In the Big Rip, the universe doesn't end in fire or ice, but in dissolution. Everything gets torn apart by runaway expansion, until even the fabric of spacetime itself shreds. The universe ends not with a bang or a whimper, but with a rip. Now, I should stress that the Big Rip is speculative. It depends on the nature of dark energy, which we don't understand. If dark energy is constant, what's called a cosmological constant, then we get a less dramatic, but still bleak scenario called heat death. In heat death, the universe expands forever, cooling as it goes, until eventually all the stars burn out, all the black holes evaporate, and the universe reaches a state of maximum entropy, a cold, dark, featureless expanse where nothing ever happens again. Either way, the long-term prognosis for the universe is not great. Expansion, driven by dark energy, appears to doom us to an eternally expanding, ever more isolated existence. The universe will not end dramatically. It will just fade, slowly, over incomprehensible timescales. But here's the thing. These are predictions based on our current understanding, which is admittedly incomplete. Dark energy remains one of the biggest mysteries in physics. We don't know what it is or whether it will remain constant. It's possible, though we have no evidence for this, that dark energy could change in the future, or that some new physics could alter the universe's trajectory. And even if the standard scenarios are correct, we're talking about timescales so vast that they're almost meaningless. The heat death or big rip won't happen for trillions upon trillions of years, far longer than the current age of the universe. Stars will continue forming for hundreds of billions of years. Life could persist for unimaginable lengths of time before the end comes. Moreover, thinking about cosmic endings forces us to confront deep questions about meaning and significance. Does the eventual fate of the universe rob our existence of meaning? I'd argue the opposite. The fact that we exist at all in this narrow window of cosmic time, aware of our place in an expanding universe, is itself profoundly meaningful. We are the universe becoming aware of itself. We are stardust contemplating the stars. And that brings me to the heart of what I want you to take away from this discussion. Yes, the universe is expanding. Yes, distant galaxies are receding faster than light. Yes, we're living in a cosmos with horizons we can never cross, moving toward a future that's ultimately beyond our control. But none of that diminishes the wonder of it all. If anything, it enhances it. We live in a universe where space itself is a dynamic entity, where the fabric of reality is constantly evolving, where the very distances between objects are not fixed but changing. We live in a cosmos that had a beginning and will have an end, a cosmos that's just old enough for us to understand it and just young enough for us to see it in all its glory. Think about how extraordinary that is. For billions of years, the universe evolved in darkness, unobserved. Then, on at least one small rocky planet orbiting an ordinary star, matter organized itself into forms capable of perception, thought, and understanding. And those forms us built tools to extend our senses across billions of light years, capturing photons that have been traveling since before our planet existed, and from those photons, reconstructing the history and structure of the entire universe. We figured out that the universe is expanding. We've measured how fast. We've looked back in time to see the Big Bang's afterglow. We've discovered dark energy and cosmic horizons and the possibility of a multiverse. We've unraveled the paradox of faster-than-light expansion and understood how it fits with Einstein's relativity. This is humanity's greatest achievement. Not our technology, not our art, but our understanding. Our ability to take the limited information available to us light from distant galaxies, the glow of the CMB, the tick of atomic clocks, and from that, build a coherent picture of a universe 13.8 billion years old and 93 billion light years across. And we're not done. We're still figuring things out. We still don't know what dark energy is, or what dark matter is, or what happened at the very beginning of the Big Bang, or whether there are other universes beyond our horizon. These are questions for the next generation of physicists and cosmologists to tackle. Maybe some of you watching this will be part of that effort. But even with what we know now, we can see that we live in a universe far stranger and more wonderful than anyone imagined even a century ago. A universe where the speed of light is both an absolute limit and a surmountable barrier, depending on how you look at it. A universe that's simultaneously finite and possibly infinite, bounded and unbounded, observable and unobservable. All right, we've covered a ton of ground, and I want to make sure you're still with me. Let me quickly recap the journey so far Before we push into even deeper territory, we started with the paradox. Light is the speed limit, but galaxies are receding faster than light. We learned that this isn't actually a contradiction, because the speed limit applies to motion through space, not to space itself expanding. We explored what space really is, not just emptiness, but a physical entity that can expand, curve, and vibrate. We discovered that the universe is not just expanding, but accelerating, driven by mysterious dark energy. We learned about cosmic horizons and how parts of the universe are forever beyond our reach. We traced the expansion back to the Big Bang and forward to possible ultimate fates like heat death or the Big Rip. And through all of this, we've seen that faster-than-light expansion is not just an obscure technicality. It's fundamental to understanding the cosmos. It shaped the early universe during inflation. It determines what we can see today. It will govern the universe's far future. Now, I want to take you deeper, because there's still more to this story, and it's about to get even more mind-bending. We need to talk about the nature of time itself, about what it means for causality in an expanding universe, and about some truly wild implications that most people never think about. Stay with me. The best parts are still coming. Let's talk about time. Because cosmic expansion doesn't just affect space, it profoundly affects our understanding of time as well. And when you really dig into what expansion means for time, you start to realize that our intuitive understanding of past, present, and future breaks down in deep and unsettling ways. Here's the basic issue. In special relativity, there's no absolute notion of now for observers who are far apart and moving relative to each other. What you consider to be happening right now at a distant location depends on your state of motion. This is called the relativity of simultaneity, and it's one of the weirdest consequences of Einstein's theory. For example, imagine you're on Earth, and there's an alien on a planet 10 light years away. If you're both at rest relative to each other, you might agree on what's happening now on each other's planets. But if the alien starts moving toward Earth at high speed, events that are in your future become part of their present. And if they move away from you, events in your past become their present. This is deeply weird, but it's been confirmed by countless experiments. Time is not absolute. It's relative to the observer. Now, add cosmic expansion into the mix, and things get even stranger. When we talk about the age of the universe being 13.8 billion years, what we mean is that's how much time has passed for an observer who's been moving along with the expansion, what's called a comoving observer. If you've been sitting still relative to the cosmic microwave background, not moving toward or away from distant galaxies, then you've experienced 13.8 billion years since the Big Bang. But what if you haven't been sitting still? What if you've been traveling at high speeds? Then you've experienced less time. This is time dilation again. A hypothetical traveler moving at near light speed since the Big Bang might have experienced only a few million years of time, even though 13.8 billion years have passed for the rest of the universe. This raises a bizarre question. What does it mean to say the Big Bang happened 13.8 billion years ago? For whom? The answer is, for comoving observers. For someone moving differently, the answer would be different. But here's where it gets really wild. Because of cosmic expansion, distant galaxies are receding from us. And in a very real sense, they're moving through time differently than we are. Now, this doesn't mean time is passing faster or slower for them locally. They experience time normally, just like we do. But when we try to define a global now across the entire universe, we run into problems. Think about it. If a galaxy is currently 10 billion light years away from us, what does currently mean? We see that galaxy as it was 10 billion years ago when the light left it. But during those 10 billion years, the galaxy has been receding due to expansion. So where is it now? And what is happening there now? There's no single right answer to this question. Different ways of slicing spacetime into space at different times give different answers. Cosmologists use something called comoving coordinates, where now is defined as surfaces of constant time since the Big Bang. But this is a choice, not a fundamental truth. Here's an analogy. Imagine you have a loaf of bread and you want to slice it. You could slice it straight across, perpendicular to the length of the loaf. Or you could slice it at an angle. Either way, you're getting slices of bread, but the slices look different depending on how you cut. Space-time is like that loaf. There are many ways to slice it into space at different times, and they're all equally valid. This might sound like a technical issue for cosmologists to worry about, but it has profound implications. It means that the notion of a global now across the universe is somewhat arbitrary. What we call the present moment is not a fundamental thing. It's a choice of how to slice space-time. And here's where faster-than-light expansion makes this even more mind-bending. For galaxies beyond our cosmic horizon, there's a sense in which our now doesn't extend to them at all. We're so causally disconnected that the notion of simultaneity breaks down completely. Events happening now in those galaxies are not part of our present, our past, or even our future in any meaningful sense. They're just elsewhere, disconnected. This raises deep questions about the nature of existence and reality. If events are causally disconnected from us, in what sense do they exist? This isn't just philosophy. It's a real question that physicists grapple with. Some physicists, like Max Tegmark, have argued for what's called the mathematical universe hypothesis, the idea that the universe is, fundamentally, a mathematical structure, and everything that exists is simply that which is mathematically consistent. In this view, causally disconnected regions of spacetime are just as real as the region we inhabit. They're just different parts of the same mathematical structure. Others argue for a more operational view. Reality is what can be observed or interacted with, either directly or indirectly. In this view, regions beyond our cosmic horizon might exist in some abstract sense, but they're not part of our reality. There's no consensus on this. It's genuinely unclear what it means for something to exist if it's forever beyond the reach of observation or influence. But let me bring this back to something more tangible, the actual experience of living in an expanding universe. Because even though cosmic expansion is happening everywhere, we don't feel it. We don't notice it in our daily lives. Space isn't expanding inside your room, inside the solar system, or even inside the galaxy. So what would it actually be like to experience cosmic expansion directly? There's a thought experiment that addresses this. Imagine you're floating in intergalactic space, far from any galaxies. You have a friend floating nearby, let's say a kilometer away. In an expanding universe, the space between you and your friend is expanding. Over time, you'll drift apart, even though neither of you is moving through space. You're both at rest, but the distance between you is increasing. Now, a kilometer is such a tiny distance on cosmic scales that this expansion would be imperceptibly slow. At the current expansion rate, you and your friend would drift apart by about 1/10,000,000,000th of a meter per year. You'd never notice. But here's the thing. You could, in principle, counteract this drift by just gently pushing toward each other occasionally. The expansion of space at small scales is so weak that any force, even the slightest push, can overcome it. This is why bound systems like galaxies, solar systems, and atoms don't expand. The forces holding them together are far stronger than the gentle push of cosmic expansion. But imagine you're much farther apart, say, 1,000,000,000 light years apart. Now the expansion between you is significant. And if you're far enough apart, you're receding faster than light. At that point, no force can bring you back together. Even if you both started traveling toward each other at the speed of light, the space between you would be expanding faster than you could cross it. You'd never meet. You'd be causally disconnected forever. This is the reality of living in an expanding universe. Distance doesn't just mean space between objects. It means possibility or impossibility of connection. Beyond a certain distance, connection becomes literally impossible. Not just difficult, impossible. The laws of physics forbid it. And here's what should really blow your mind. That critical distance is shrinking. As the universe's expansion accelerates, the cosmic horizon is getting closer. Right now, we can see galaxies about 46 billion light-years away. But galaxies we can see today might be impossible to reach, even if we left toward them right now at the speed of light. They're beyond what's called our particle horizon, the boundary of the region we could ever reach, even in principle. In fact, most of the galaxies we can see are already beyond our particle horizon. We can see them because we're receiving light they emitted billions of years ago when they were closer. But if we tried to travel to them, we'd never arrive. Space is expanding too fast. Let me give you some numbers to make this concrete. The current cosmic horizon, the boundary of the observable universe, is about 46 billion light-years away. But the particle horizon, the boundary of what we could ever reach, is only about 16 billion light-years away. Everything beyond that 16 billion light-year mark is forever beyond our reach. This means that more than 90% of the observable universe is inaccessible to us. We can see it, but we can never go there. Ever. No matter what. Think about how strange that is. We can observe galaxies, study them, measure their properties, learn about their histories, but we can never visit them. They're like mirages in the desert, visible but unreachable. Except these mirages are real. They're just on the wrong side of an impassable barrier created by the expansion of space. Now, you might be wondering, if we can never reach those galaxies, do they even matter? Why should we care about them? There are lots of reasons, but here's one that's particularly compelling. Those distant galaxies tell us about conditions in the early universe that we can't study any other way. When we look at a galaxy 12 billion light-years away, we're seeing it as it was 12 billion years ago, when the universe was only 1.8 billion years old. These galaxies are fossils, preserved in light, showing us what the universe was like in its youth. By studying galaxies at different distances and therefore at different points in cosmic history, we can piece together how galaxies form and evolve over time. We can see how the universe changed from a smooth, nearly featureless expanse after the Big Bang to the rich, structured cosmos we see today. In other words, we can use light travel time and cosmic expansion to turn our telescopes into time machines. Looking outward in space is looking backward in time. The farther we look, the farther back we see. This is one of the most powerful tools in cosmology, and it's made possible by the combination of the finite speed of light and the expansion of the universe. If light traveled infinitely fast, we'd only see the universe as it is now. If the universe weren't expanding, we couldn't use distance as a proxy for time. But because light is finite and the universe is expanding, we have a window into cosmic history. And here's something beautiful. That window is closing. As expansion accelerates, more and more of the universe will slip beyond our cosmic horizon. In the far future, cosmologists will have less to observe, less data to work with. We're living in the golden age of cosmology, a time when the universe is old enough to be interesting, but young enough to be observable. All right, let's shift gears and talk about something that might seem like science fiction, but is actually deadly serious: the possibility of faster-than-light travel. Because if space itself can expand faster than light, does that open up any loopholes for faster-than-light travel? The short answer is maybe, possibly. It's complicated. Here's the idea. What if, instead of trying to move faster than light through space, we manipulated space itself? What if we could make space contract in front of a spacecraft and expand behind it, creating a bubble of normal space that carries the spacecraft along? The spacecraft wouldn't be moving through space faster than light from its own perspective. It might not be moving at all, but the bubble of space around it would be moving, carrying it along for the ride. This is called an Alcubierre drive, named after physicist Miguel Alcubierre, who proposed it in 1994. And here's the shocking thing. It's consistent with general relativity. The equations allow it. You could, in principle, travel from Earth to Alpha Centauri in a matter of days or weeks, even though it's 4.37 light years away, without ever moving faster than light through the space inside your bubble. Before you get too excited, there are massive problems with this idea. First, to create the necessary warping of space, you'd need exotic matter with negative energy density. We've never seen such matter in nature, and it might not exist. Second, even if it does exist, the amount you'd need is astronomical. Some calculations suggest you'd need more energy than exists in the entire observable universe. Third, there are causality issues. You could potentially use an Alcubierre drive to travel backward in time, which creates all sorts of paradoxes. So while the Alcubierre drive is theoretically possible within general relativity, it's almost certainly not practical. It's more of a mathematical curiosity than a viable technology. But here's why it's interesting for our discussion. It shows that the cosmic speed limit is not as absolute as it might seem. With the right manipulation of spacetime, you can get from point A to point B faster than light would take to travel through flat space. The universe provides loopholes. Expansion is one, and exotic spacetime curvature is another. This raises a deeper question. What exactly is the cosmic speed limit limiting? It's limiting the speed of objects moving through spacetime, and it's limiting the speed at which information can be transmitted. But it's not limiting the ways spacetime itself can change. Think of it this way. The rules of chess limit how pieces can move. A bishop can only move diagonally, a rook only vertically or horizontally. But those rules don't limit what you can do with the board itself. You could pick up the board and turn it around, and suddenly your bishop is pointing in a different direction, even though it never moved according to the rules. Similarly, the cosmic speed limit governs motion through spacetime, but it doesn't govern how spacetime itself can be manipulated. And that's what cosmic expansion is, a manipulation of spacetime. It's the universe picking up the board and stretching it. Now, there's another related idea that's worth mentioning: wormholes. A wormhole is a hypothetical tunnel through spacetime that connects two distant points. If you could create a wormhole, you could step through and emerge light years away, traveling no faster than light from your own perspective, but covering vast distances through the shortcut. Like the Alcubierre drive, wormholes are allowed by general relativity, but they come with huge practical problems. They'd require exotic matter to stabilize them. They'd likely be unstable and collapse before you could travel through, and they might allow time travel with all the associated paradoxes. But here's the thing. Both Alcubierre drives and wormholes exploit the same loophole that cosmic expansion exploits. They manipulate spacetime itself rather than moving through it. And the fact that general relativity allows these solutions suggests that the universe is more flexible than we might think. Whether any of these exotic spacetime manipulations are actually possible in nature is an open question. Most physicists are skeptical, but the mathematics says they're at least conceivable, and that's fascinating in itself. What this tells us is that the cosmic speed limit is about local physics. If you're sitting next to a light beam, you can never catch up to it. That's inviolable. But on larger scales, where spacetime itself can change, there's more flexibility. The universe is not a rigid, unchanging stage. It's a dynamic arena that can be shaped, at least in principle, in ways that allow for outcomes that seem impossible from a naive perspective. And cosmic expansion is the most dramatic example of this. It's not some exotic, hypothetical phenomenon. It's happening right now, all around us, carrying distant galaxies faster than light without violating any of Einstein's rules. Now, I want to address a question that might have been bugging you this whole time. If all this is true, why didn't anyone figure it out until the 20th century? Why did it take so long to discover that the universe is expanding? The answer is simple. Cosmic expansion is only detectable over vast distances. On small scales, even on the scale of our galaxy expansion, is completely negligible. It wasn't until we developed telescopes powerful enough to see distant galaxies and techniques sensitive enough to measure their motions that we could detect expansion at all. Edwin Hubble's discovery in 1929 was only possible because he had access to the largest telescope in the world at the time, the 100-inch Hooker telescope on Mount Wilson. And even then, his measurements were difficult and uncertain. It took decades of further observations to confirm that the expansion was real and to measure it precisely. And discovering that the expansion is accelerating took even longer because the effect is subtle. You have to look at very distant supernovae and measure their brightness and redshift with extreme precision. It wasn't until the 1990s, with space-based telescopes and advanced digital cameras, that this became possible. So the reason we didn't know about cosmic expansion earlier isn't that people weren't smart enough. It's that we didn't have the tools to see it. The universe kept this secret until we developed technology sophisticated enough to uncover it. And here's what should humble us. There are probably other secrets the universe is keeping that we don't have the tools to uncover yet. Things that will seem obvious in hindsight once we discover them, but which are completely hidden from us now. What might those secrets be? We don't know. That's the nature of the unknown, but we have hints. Dark matter and dark energy are obvious candidates. We know they exist, but we don't know what they are. The mystery of quantum gravity is another. We need a theory that combines quantum mechanics and general relativity, but we don't have one yet. And there might be deeper mysteries we haven't even imagined. Nature has surprised us before, and it will almost certainly surprise us again. But here's the wonderful thing. We keep pushing forward. We keep building better telescopes, more sensitive detectors, more powerful theories. We keep asking questions and refusing to accept ignorance. And slowly, bit by bit, we're peeling back the layers of mystery, revealing the deep structure of reality. The discovery that the universe is expanding, and that this expansion can be faster than light without violating relativity, is one of the great triumphs of human intellect. It took observations, mathematics, and deep thinking to put the pieces together. And now we understand something about the cosmos that no one even suspected a century ago. That's the power of science. It's not just a collection of facts. It's a method for uncovering truths about reality that are hidden beneath the surface. It's a way of looking at the universe that reveals its secrets, one by one, through careful observation and rigorous reasoning. And you're part of that. By learning about this, by grappling with these ideas, by letting your mind expand to encompass the vastness and strangeness of the cosmos, you're participating in humanity's greatest intellectual adventure. We're almost there. We've covered so much ground, and there's just a bit more to explore before we bring this all together. Stay with me. The final revelations are coming, and they're going to tie everything together in a way that will leave you with a profound new understanding of the universe and your place in it. Let's talk about something deeply personal. How does all of this, the expansion of the universe, faster than light recession, cosmic horizons, affect you? Why should you care about these abstract concepts? What do they mean for your life, your worldview, your sense of self? These aren't trivial questions. Understanding the cosmos changes how you see everything. It changes your perspective on what matters, on how you fit into the grand scheme of things, on the nature of existence itself. First, consider this. You are made of atoms forged in the hearts of stars. Every carbon atom in your body, every oxygen molecule you breathe, was created in a stellar furnace billions of years ago. Those stars lived, burned, and died in spectacular explosions called supernova, scattering their enriched material into space. That material coalesced into new stars, planets, and eventually, you. You are, quite literally, stardust. You are the universe experiencing itself. And the fact that you can know this, that you can trace your origins back to the Big Bang, through generations of stars, to the planet, and the life that emerged on it, is extraordinary. But here's where cosmic expansion makes this even more profound. The atoms in your body have been on a journey of almost 14 billion years. They've traveled vast distances, been part of multiple stars, witnessed the formation of galaxies, and somehow ended up here, arranged in a pattern that can think, feel, and wonder about its own existence. And the universe those atoms traveled through was expanding the entire time. The distances they covered are not the same as they would be today, because space itself has grown. The universe your atoms experienced was smaller, denser, hotter than it is now. In a very real sense, you are a product of cosmic expansion. Without it, the universe would have collapsed long ago, and you wouldn't exist. Expansion is not just some abstract phenomenon happening at the edges of the observable universe. It's part of the story of how you came to be. It set the stage for stars, galaxies, and ultimately life. You exist because the universe is expanding. Now, think about what cosmic expansion means for meaning itself. Some people find the idea of an expanding, accelerating universe depressing. They think it makes everything seem pointless. If the universe is ultimately headed for heat death or the Big Rip, if everything we build will eventually decay into nothing, what's the point? But I'd argue the opposite. The fact that the universe has an ultimate fate doesn't rob the present of meaning. It amplifies it. Meaning doesn't come from permanence. It comes from mattering in the moment, from connection, from experience, from the difference you make in the lives around you. You're here now, in this brief window of cosmic time when the universe is observable and understandable. You have the capacity to wonder, to learn, to create, to love. That's not diminished by the fact that it's temporary. If anything, it's made more precious. And the fact that you're watching this video, that you've stuck with me through this entire journey, means you're curious. You want to understand. You're willing to let your mind stretch to encompass ideas that don't fit with everyday experience. That curiosity is precious. Nurture it. Follow it wherever it leads. Because that curiosity is the same force that led humans to look up at the stars and wonder, to build telescopes and spacecraft, to develop mathematics and physics, to uncover the deep truths about reality that we've been discussing. You're part of that tradition. You're a link in the chain of understanding that stretches from ancient astronomers watching the sky to modern cosmologists mapping the universe. And every time you learn something new, every time you have an insight, every time you share what you know with others, you're adding to that chain. All right, we're in the home stretch now. Let's bring this all together and talk about what it all means. We've covered the science, the math, the history, the implications. Now let's step back and see the big picture. The universe is expanding. That expansion can carry distant galaxies faster than light without violating the cosmic speed limit, because the limit applies to motion through space, not to the expansion of space itself. This expansion has shaped the universe from the Big Bang to today and will determine its ultimate fate. It's fundamental to understanding cosmology, and it reveals deep truths about the nature of spacetime, causality, and existence. But more than that, it reveals something about the universe's character. The cosmos is not static or eternal in the sense our ancestors imagined. It had a beginning. It's evolving. It will have an end, or at least a transformation into something unrecognizable. And yet, within that cosmic story, there's room for complexity, for structure, for life, for consciousness. The universe didn't have to be this way. It could have collapsed immediately after the Big Bang. It could have expanded so fast that no structure ever formed. It could have been governed by laws that didn't allow for stable atoms or chemistry or evolution. But it's not. The universe is, in some sense, fine-tuned for complexity. The expansion rate is just right fast enough to avoid collapse, slow enough to allow galaxies to form. The fundamental constants are just right. The strength of gravity, the mass of the electron, the charge on the proton. Change any of these by a small amount, and the universe would be sterile, unable to support life. Whether this fine-tuning is a coincidence, evidence of a multiverse where we happen to be in a hospitable universe, or something else entirely, is an open question. But it's undeniable that we're extraordinarily lucky to exist in this particular universe with these particular laws. And the expansion of the universe is part of that luck. Without expansion, we wouldn't be here. The universe needs to expand for stars to form, for galaxies to separate into distinct structures, for the conditions that allow life to emerge. So when we say the universe is expanding faster than light, we're not just stating an abstract fact. We're pointing to a fundamental feature of the cosmos that made our existence possible. Think about that. The very phenomenon that seems most divorced from everyday life, cosmic expansion, is actually intimately connected to why you're here. It's part of the story of how the universe went from a hot, dense, nearly uniform state to a rich, complex cosmos with stars, planets, and life. You're a beneficiary of cosmic expansion. You wouldn't exist without it, and now you understand it. You've completed the loop the universe created you, and you've figured out how it did it? That's beautiful. That's profound. And it should fill you with a sense of awe and connection. Now, let's talk about the future. We've discussed possible fates for the universe heat death, Big Rip, or something else. But what does that mean for humanity, for life, for consciousness? In the short term, meaning the next few billion years, we're fine. The sun will continue shining. Earth will remain habitable. Life can continue evolving. And if we're smart, humanity will spread beyond Earth, colonizing the solar system and eventually reaching other stars. In the medium-term tens to hundreds of billions of years, things get harder. Stars will gradually stop forming as the universe's supply of hydrogen is used up. Galaxies will fade. The universe will get darker and colder. But there will still be plenty of time for civilizations to thrive, build, explore. In the long-term trillions of years and beyond, the outlook is bleak. Heat death or the Big Rip will eventually render the universe inhospitable. All structure will decay. All complexity will unravel. But here's the thing. Those timescales are so vast that they're almost meaningless. Trillions of years is longer than the current age of the universe, multiplied by itself hundreds of times over. It's a span of time so long that trying to comprehend it is futile. And a lot can happen in that time. Civilizations could rise and fall countless times. Life could spread across galaxies. New forms of existence we can't even imagine could emerge. Moreover, our predictions about the far future are based on our current understanding of physics. But physics is always evolving. We're discovering new things all the time. It's entirely possible that future physics will reveal possibilities we haven't dreamed of, ways to harness dark energy, ways to access other regions of the multiverse, ways to persist even as the universe expands forever. I'm not saying we should be complacent. Understanding the ultimate fate of the universe is important, but we shouldn't let far future concerns overshadow the immediate reality. We're here, now, in a universe full of possibilities, and we have work to do. That work includes continuing to explore the cosmos, to push the boundaries of knowledge, to ask questions and seek answers. Every generation builds on the last, adding to our collective understanding. And the questions we're asking today about dark energy, cosmic expansion, the nature of spacetime, will be answered by future generations, just as we've answered questions our ancestors asked. And who knows? Maybe one of you watching this will be part of that process. Maybe you'll become an astronomer, a physicist, a cosmologist. Maybe you'll make a discovery that shifts our understanding of the universe. Maybe you'll be the one to solve the mystery of dark energy, or figure out what happened at the Big Bang, or discover evidence of a multiverse. Or maybe you won't become a scientist, but you'll take what you've learned here and share it with others. You'll help spread understanding, inspire curiosity, and keep the flame of knowledge burning bright. Because that's what this is all about, ultimately. Not just accumulating facts, but understanding. Not just knowing that the universe is expanding, but grasping what that means, why it matters, how it connects to everything else. You've done that today. You've taken a journey from the cosmic speed limit to faster-than-light expansion, from the Big Bang to the ultimate fate of the universe, from abstract physics to personal meaning. You've stretched your mind to encompass ideas that challenge intuition and expand possibility. And you're different now than you were at the start. You see the universe differently. You understand something profound about reality. You're part of the small fraction of humanity that truly grasps how strange and wonderful the cosmos is. That's an achievement. That's something to be proud of. And it's something to build on. So here's my challenge to you. Don't stop here. Keep learning. Keep asking questions. Keep wondering. The universe is vast and strange and beautiful. And there's always more to discover, more to understand, more to be amazed by. And share what you know. Talk to people about this stuff. Help others see what you've seen. Because knowledge isn't meant to be hoarded, it's meant to be spread. The more people who understand the universe, the better off we all are. We're living in a remarkable time, a golden age of cosmology, when the universe is both observable and comprehensible. The age of space telescopes and gravitational wave detectors and cosmic microwave background maps. The age when humans are figuring out how the universe works at the deepest levels. Be part of that. Contribute to it. Celebrate it, because the universe is expanding. Galaxies are flying apart. The cosmos is evolving toward an uncertain fate. But right here, right now, in this brief moment of cosmic time, we have the chance to understand it all, to see the big picture, to know our place in the grand scheme. That's a privilege. That's a gift. And it's ours to embrace. So let me leave you with this. The speed of light is the cosmic speed limit. Nothing can move through space faster than light. But space itself can expand at any speed, carrying distant galaxies faster than light in the process. This is not a violation of relativity. It's a loophole, a wrinkle in the fabric of spacetime that allows for outcomes that seem impossible but are perfectly consistent with the laws of physics. And understanding this, truly understanding, it changes everything. It changes how you see the night sky, how you think about distance and time, how you conceptualize your place in the universe. You live in an expanding cosmos where galaxies race away from each other, where space itself is a dynamic entity, where the past is observable and the future is uncertain. You live in a universe that had a beginning, that's evolving, that will have an end or transformation beyond recognition. But you also live in a universe that's comprehensible, beautiful, governed by simple mathematical laws that can be discovered and understood. And you're capable of that understanding. That's the final revelation. The universe is not just expanding, we're expanding with it. Not physically, but mentally, intellectually, spiritually. Every time we learn something new, every time we push back the boundaries of ignorance, we're growing, evolving, becoming more than we were. The universe is on a journey from simplicity to complexity, from uniformity to structure, from ignorance to understanding. And we're part of that journey. We're how the universe knows itself, how it wakes up and becomes aware. So yes, the universe expands faster than light in some regions. But it also expands in understanding, in consciousness, in meaning. And that expansion, the growth of knowledge and awareness, is just as important, just as profound as the physical expansion of space. You're part of both. You're a physical being, made of atoms forged in stellar furnaces, living in an expanding universe. But you're also a conscious being, capable of understanding that universe, of seeing the patterns, of grasping the deep truths. That's what makes you special. That's what makes all of this matter. The universe is vast, ancient, and strange. But it's also knowable, and you've taken a step toward knowing it. You've looked at one of the deepest mysteries. How can things move faster than light without violating the cosmic speed limit? And you've understood the answer. Space itself expands. That's the key. That's the revelation. And from that simple fact flows a cascade of implications about the nature of reality, the structure of the cosmos, and our place within it. You're no longer ignorant of this. You're enlightened. You've seen a glimpse of the universe as it really is, not as common sense suggests it should be. Hold on to that. Build on it. Let it inspire you to keep learning, keep questioning, keep exploring. Because the universe has more secrets to reveal, more mysteries to solve, more wonders to discover. And you're part of the generation that's going to discover them. The journey doesn't end here. It never ends. There's always more to learn, always deeper truths to uncover. But you've taken an important step on that journey today. You've expanded your understanding. You've seen the cosmos in a new light, and that's something no one can take away from you. You carry that knowledge now. It's part of you, and it will shape how you see everything from this moment forward. So go forth with that knowledge. Share it, use it. Let it inspire you. And never stop wondering about the universe and your place in it. Because wonder is the beginning of wisdom. And wisdom is the goal of all human endeavor. The universe is expanding faster than light. And now you know why, how, and what it means. Welcome to a deeper understanding of reality. Welcome to the cosmos as it truly is. And thank you for taking this journey with me. It's been a privilege to share this with you. Now go out there and look at the stars with new eyes. See the expansion. Feel the connection. Embrace the wonder. The universe is waiting for you.